In this video, we're going to talk about unstressed vibration analysis. And from a higher level, the purpose behind any vibration analysis is to determine the frequencies and corresponding mode shapes of vibration. Now, for an unstressed vibration analysis, we're looking at the unstressed state of the model, and we're looking to determine the natural frequencies, basically the frequency for which a model or an element or whatnot will oscillate at without any external loading or damping or those sorts of things. And this is extremely important when we want to look into further analysis that might consider seismic loading, resonance of some sort. We want to understand the resonance threat or footfall, machinery-induced vibration, you name it. Basically, any situation where we have some load that varies with time, it's very important that we understand the natural frequency and the various mode shapes. Another useful reason for vibration analysis is it's useful for spotting modeling errors early in your modeling process. Before you've even applied your loads, you can go ahead and run a vibration analysis, and you'll be able to determine whether or not certain elements might not be connected as you intended, or perhaps maybe the model is more or less stiff, or the mass is modeled incorrectly. Those sorts of things can be spotted with a vibration analysis. Now, on the higher level here, basically, vibration analysis is a function of mass and stiffness. So if you increase the stiffness, the frequency will increase. If you increase the mass, the frequency will decrease. And for that reason, the stiffness and the mass must be modeled accurately. Now, the stiffness itself can be defined using your existing members and the section properties assigned. You can even define springs and 1 and 2 noded springs. However, mass modeling does require a little bit more thought. There's system mass, and in the case of system mass, SRAM will automatically include the self-weight in your system mass. However, if you don't want that to happen, you need to assign a zero density material to whatever elements are contributing to the self-weight. And you can do that by defining your own material and just defining a force density of 0. Another way of defining your mass is using lump masses, which are basically ways of explicitly modeling mass at a specific joint with your desired magnitude in a certain direction. So it's a way of simplifying the mass modeling, and it helps control which degrees of freedom are active during a vibration analysis. You can also convert loads to mass. So imagine that you have your normal model, and you've assigned a load case that might represent a fairly large portion of mass. Perhaps it's equipment on a pipe rack or something like that. Well, you could go ahead and convert that load to a mass for vibration analysis, and that will then contribute to the mass matrix being used during the vibration analysis and could affect the results. Now, from a vibration analysis, we get mode shapes. And the number of mode shapes is equal to the number of free degrees of freedom that have assigned mass. So this may be sounding a little bit strange from what we've discussed so far, but basically you can think of every single joint in a 3D model will have 6 degrees of freedom by default. So it will have X, Y, and Z translation and X, Y, and Z rotation. However, once you start adding supports to those joints, you remove some of those degrees of freedom from the dynamic analysis problem. Also, if you're assigning lump masses that may only have mass in certain directions, that will dictate which degrees of freedom are participating in this particular mode shape calculation. So there can be a lot of different modes within your model because it might have a large number of degrees of freedom. Now, for the purposes of seismic analysis in general, only modes with a large percentage of the mass participating are really considered to be important. This will vary depending on the engineer and the situation, but for the most part, I think that holds true. And the reason being is that there could be thousands of mode shapes that exist, and they may not all be useful to us, and nobody really has the time to go through every single mode shape and examine them all at once. Now, we talk about this a lot more in our A301 Dynamics for Structural Engineers course, and I should also mention our A501 Seismic Analysis training course. We're just really going to be scratching the surface of this topic, and I would say if you're interested in dynamics or seismic analysis, to check out those other courses since they'll go into a lot more detail. Now for this particular example, we're going to use a fairly simple model. So let me just use this one here. If we look at the supports, I have fully fixed supports at the base of both columns. I've also got a joint at the center of my beam. And if I just shrink the elements, you can see that it's not an analytical model. We have a physical member basically going along the entire length of this beam. But as you can see here, we have 3 joints at the top above our supports, and so these ones aren't being constrained currently. And as we mentioned earlier in the slides, by default, SRAM is going to be including the self-weight and the system mass for us. However, I've gotten around that by defining my own material. I have 2 materials in this model. I have a steel US and Canada, which we're used to already, and I have the 0D steel. And if I just right-click on my material properties, I can see the difference between these. So steel US and Canada has all the default properties. The 0D one has all the same properties except for the force density equals to 0. And that means that these members won't have any mass to them during this vibration analysis. We'll have to assign our mass some other way. And so you can see that they're assigned currently to the members. So we have to assign the mass using lump masses. So I have the lump mass tool here, and you can see that I've actually got a lump mass already added to this beam. It's a 100 kilonewton lump mass in the X force direction. So this is being applied a lot like a load in this situation, but it actually represents mass. And it's being applied to the center of this beam here. So right now, because I only have, my members don't have any self-weight themselves, and I only have one lump mass in the X force direction, these joints don't have any lump mass on them. That means that this is the only joint with any mass associated with it in the entire model, and it's only applied in 1 degree of freedom. So that means I only have 1 degree of freedom with any dynamic mass associated with it. So this can be thought of right now as a single degree of freedom system. So I'm going to go ahead and run an unstressed vibration analysis. So click Analyze, and I'm going to go with unstressed vibration. And with the unstressed vibration analysis here, we have similar parameters to what we've seen already with buckling analysis. So we have different parameters for different eigenvalue extraction methods, which we have at the base here. I have subspace iteration and Jacobi threshold, which we'll be looking into. You can see that I have a number of iterations, just like buckling or nonlinear analysis, a tolerance, and I also have a number of eigenvalues or mode shapes that I'd like to extract. And I can convert loads to mass here if I wanted to. So right now, I'm just going to go with 1 eigenvalue. It is a single degree of freedom system, so I can only select 1. That's 1 mode shape. And I'm going to use the subspace iteration model, which we'll look into more in just a second. But basically, the subspace iteration model is more intended for large models where you might have lots of degrees of freedom. I'll press OK to run the analysis now. And we can see here that when we run the analysis, we actually run into an issue. We get this error SI007, requested number of eigenvalues is too large. And it's letting me know here that the maximum possible eigenvalues is 0, but I've actually requested 1. And in order for this to work, I would have to have at least 2 eigenvalues within my model. So this is actually running into one of the properties of the subspace iteration eigenvalue extraction method. Subspace iteration requires twice as many eigenvalues to exist as what we've requested. And because we just have a single degree of freedom system, that means that we only have 1 degree of freedom that exists. So we can't request less than 1 degree of freedom, or 1 eigenvalue, sorry. So we can't actually use the subspace iteration method for this particular model. It doesn't work for single degree of freedom systems. We'd have to use the Jacobi threshold method. And this is better for small models. It's more computationally expensive. It puts your computer through a little bit more stress. But it's more important for us to find all the modes in the model than we would want to use this method. Now for a small model like this, I don't think you would notice much of a difference in performance, but as your models get larger, you're going to be maybe wanting to consider using the subspace iteration method, especially since usually the lower half of your mode shapes are the ones of most importance. So I'm going to go ahead and choose the Jacobi threshold method. I'm still going to use one eigenvalue, and I'm just going to click OK to run the analysis. And you can see here that we're getting a clean solution. The software has gone through several different sweeps to determine the mode shapes within our model using an eigenvector analysis that we selected. And within this here, I can view my mode shape. I can see the period in the drop-down list, and I can choose the mode shape tool that we used in the buckling analysis. The same tool is active for vibration, and I can animate this particular mode shape. You'll notice here that's reporting a mass X percentage. So this is a measure of how much of the mass is moving at the same time in any direction. And when we animate this, we can see here that when I applied that 100 kilonewton lump mass, I didn't apply it as a positive or a negative. The direction will be actually arbitrary. It only cares about the actual degree of freedom that it's been applied in this case, X force. Now we talked about system mass, which in this case includes the self-weight plus any of our lump masses. And we'd have to intentionally add other loads to our model. We can actually study the masses in our model and look at other results in the numerical results window. Here I can see the frequency spreadsheet, and I can see the frequency in hertz is 5.475 hertz, 34.4 radians per second, and my period is 1.83 or 0.183 seconds. And again, I have X mass percentage of 100%. Now let's look at adding a load case to our model here. So right now I've got a couple different loads. I'm going to go with this 100 kilonewton load case, and we would apply it just like any other load. So this is just in the z-axis 100 kilonewtons at the midspan of this beam, which coincidentally happens to line up with the magnitude of my lump mass. Now notice this is in the z-axis. The other load, or the lump mass, sorry, was in the x-axis. But now we're going to go ahead and we're going to run the analysis. And we're going to run an unstressed vibration analysis, but this time we're going to convert the loads to mass, and I'm just going to select my 100 kilonewton load to convert it to a mass. Now I press OK. Again, we get a clean solution. And if I look at my mode shape now, I can see that the mode shape period has increased. And if I look at the mode shape rendering here, I can see that it's moving within the y-axis this time. So now I have mass Y percentage 100%, despite the fact that I applied that joint load in the z-axis. So it's 100 kilonewtons joint load in the z-axis. I converted that to a mass. I also have a lump mass of 100 kilonewtons in the x-axis. So this is what happens when we convert loads to mass. It's going to convert those loads to a mass in all of the axes. And I can go to the numerical results spreadsheet, and I can see, look at the total mass of my model. I can see at joint number 5, I have in the x translation direction 200 kilonewtons of mass. In y translation I have 100, and z translation I have 100. So why is this important? Well, basically the z load that I applied, when it was converted to a mass, it was converted to a mass in all degrees of freedom. So in the z, y, and x degrees of freedom. And in the x direction, I also had that lump mass that was applied. So that's been added to the mass in that model. And I have other mass spreadsheets here as well that I can look at. So I can look at the active mass and see that that's also participating in this model. Now let me go to the spreadsheet window, and I'm actually going to use the spreadsheet window to remove the lump mass, just to get rid of it here. So I'm going to use a lump mass spreadsheet, and I'm just going to select this call or this row and then click delete. And now we basically have 3 degrees of freedom in our model. We've deleted that lump mass, but we have that joint load that's now converting that joint load magnitude of 100 kilonewtons in X, Y, and Z at that center joint. So now I have 3 degrees of freedom. That means I can reanalyze. And this time I can select 3 eigenvalues. So here we can see the advantages and disadvantages of each approach. If I use a lump mass method, I know exactly which degree of freedom is going to be used in my analysis, whereas if I use the convert loads to mass method, it's going to actually convert it in all degrees of freedom, so I could end up with more mode shapes. Not all of them may be of interest to me, so we have a bit more control with the lump mass method. So I'll click OK to run. Now we get a warning here just saying no load for low case 1, but I wasn't actually looking at low case 1, so that's not a problem for me. But now I can look at the results. So I can see here I have my mode shape number 1 has a period of 1.3 seconds. Mode shape number 2, 0.18 seconds. This one looks familiar. This is the same as what we had when we had our lump mass. And mode shape number 3, this is in the z-axis. So we're having every axis participate in their own way. Now I could also go and try the subspace iteration method here. Because I have more masses assigned to more joints, or more degrees of freedom, sorry. So I can choose the subspace iteration method. And if I click OK, we're going to get that same message here. Because we requested 3 eigenvalues, but we only have 3 in our model that exist, so we can't actually do this yet either. Now I'm back in the geometry window and I can look at additional nodes that might be activated. So let's do something first here. I'm just going to change the material from the zero density material back to the original default steel material, which does have a density, meaning that I'm going to be getting system mass from this material density participating as well. Now I'm going to go through a vibration analysis again. An unstressed vibration analysis using all the convert loads to mass, and I'm asking for 3 eigenvalues using the subspace iteration method. I'll press OK. This time you can see that we get a clean solution. The reason being is that because I've added the system mass from the self-weight to the model, I now have more information within, or more mass at more joints in more degrees of freedom. So here now I have 3 different mode shapes. I have mode shape number 1, which I can animate. And you can see here that it looks very similar to the Y direction mode shape that I had previously when I was using the convert loads to mass in the zero density material. I'm not quite getting 100% mass participation out of this one though. You can look at mode shape number 2. This one looks a little different. You can see here that my previous mode shape number 2 didn't look like this. It was actually an X translation oscillation that we had, but now this one is more of a torsional mode shape. And you can see that the mass percentage is 0 in all degrees of freedom, because if you think about this, when this joint moves in the positive Y direction, this joint opposite is going to move in the negative Y direction. And the same thing in X direction. So they're going to cancel each other out. And this time we used the subspace iteration method, and we selected 3 eigenvalues. But let's think about how many actual modes we have. Right now we've got 2 joints at the base of our model that are fully fixed in rotation and translation. So they don't have any dynamic degrees of freedom at the base. But here at the top of the model, we have 3 joints, and each one of these joints has 6 degrees of freedom. It can move, and it has mass in X translation, Y translation, and Z translation, and rotation in X, Y, and Z. So I actually have 6 degrees of freedom times 3 joints. I have 18 modes potentially that I could ask for from this model. And only Jacobi analysis can find all these modes. Now I'm going to go ahead and reanalyze this model. Going to run an unstressed vibration analysis again, but I'm going to choose the Jacobi threshold method. And I'm going to run this for 18 eigenvalues. The reason I'm using the Jacobi threshold method is that because it can extract all the eigenvalues in the model, I don't have to request twice as many as exist. So I can select 18 since I have 3 free joints with 6 dynamic degrees of freedom at each. I can press OK to run the analysis. We get a clean solution. And now if I look through the results here, I can see the number of different mode shapes and their associated periods. And we can actually view this in S-view. Maybe S-view is a better way to understand these mode shapes. And I'll be able to see what's going on. So in S-view here, I can look at each mode and see the direction that it's occurring in or oscillating in. I personally like S-view because we can also render the object view. So I can just get an idea for what each one of these looks like. Now it may be that some of these mode shapes aren't really of that much interest to us. And it would be up to us to decide which ones are important or which aren't. Now after we exit out of S-view, again, recall that there was a lot of different mode shapes, and a lot of them could be considered as noise, I guess you could say. They might not necessarily be important to us. There is an option that allows us to consider filtering these out a little bit more, though. We can go to the Settings menu, Preferences. And under the Solver tab, we can say Use Lump Mass rather than Consistent Mass Matrix. More details on this are available in SRAM's help system, or if you go and take the dynamic analysis course, you'll be able to understand these options a little bit better. But now when I do this, I can go ahead and analyze, and this is going to reduce the number of dynamic degrees of freedom here. So I'm only going to have 9 degrees of freedom now, because it's going to remove the rotational modes. And I can click OK to analyze. We have all 9 degrees of freedom have been calculated for us, or all 9 mode shapes rather. And I can look at the different mode shapes again, and I can see that some of the noise from those other mode shapes has been removed. And note that the dominant modes are still the same. There's just fewer now to sort through. And typically, but not always, the lower modes are going to be of most importance. And many design codes specify that modes must be considered to account for 90% of mass in each direction. So if I go to the numerical results window, I can tally up these columns here in each direction, and I would just have to make sure that I have 90% or more when I sum them up in each direction. It depends on your jurisdiction, what the design code says, but that's what we're used to here where I am. And more nodes will actually lead to a more accurate analysis model, but it's not necessary in vibration analysis, or it's not often necessary in vibration analysis, because that will just lead to more complex modes, which are usually higher frequency and therefore not usually the important ones when doing an analysis. But it certainly doesn't hurt to at least explore subdividing your members and understanding those mode shapes, because sometimes the mode shapes can be represented better with more nodes.